Some ventilation engineering controls are classified as general ventilation, with the word general indicating that the entire workplace is ventilated. The heating and cooling system used in your home is an example of a general ventilation system. In a general ventilation system, relatively clean air, typically from outdoors, is used to dilute contaminants and move them out of the workplace. General ventilation includes natural ventilation, which is essentially to open a window. This type of open-the-window ventilation was commonly used before air conditioning, with heat generated in the factory causing natural convection of outdoor air into the building, diluting contaminants and moving them out of the facility. Many old factories were designed to have sloped roofs to encourage this natural convection. General ventilation can also be achieved mechanically. In the case shown at right, clean air is pushed into the building through ducts and discharged near the workplace floor. This air is then pulled out of the building and exhausted through a stack. Alternatively, this air can be cleaned and recirculated to reduce heating and cooling costs. In contrast, local exhaust ventilation systems evacuate contaminated air at the source. These systems can be very large, such as the multi-canopy hood system shown here. Multiple hoods or enclosures are used to evacuate contaminated air where it is produced, or local to the source. The contaminated air passes through connecting ductwork, an air cleaner, and is then exhausted outside the facility through a stack. Air from a local exhaust ventilation system can be cleaned and then recirculated back into the facility, but this practice should be restricted to contaminants of low toxicity. Air is moved through the system by a large industrial fan. We will spend most of our time today on local exhaust ventilation systems because these systems are most effective at reducing exposures in the workplace. Local exhaust ventilation systems can also be small and self-contained. They have the same components as the larger system, a hood designed to evacuate the contaminant, in this case from a welding, connecting ductwork to move the contaminant to an air cleaner, and finally the air cleaner and an air mover. In this case, the filter and air mover are contained in a single housing. Hoods are the entry point to the ventilation system. They have unique designs to serve a given operation or process. For example, we show a canopy hood used to ventilate hot vapor from a dip tank. Hoods are effective when operated at a specific airflow rate, commonly abbreviated with the symbol Q, and measured in the duct just downstream of the hood. Connecting ductwork serves to transport the contaminant from the hood to the air cleaner. Ductwork is sized to achieve a minimum transport velocity, symbolically represented with a capital V. Minimum transport velocity depends on the type of material being conveyed. Vapors and gases are easy to move, so transport velocity can be low relative to the high transport velocities required to move heavy dusts, such as sand from casting metal. I want to make sure that we don't confuse airflow with velocity. Airflow, Q, is equal to the velocity of air in the duct, V, times the cross-sectional area of the duct, A, which can be written as Q equals V times A. Rearranging, we can express velocity as the airflow divided by area. For a round duct, cross-sectional area is equal to pi over 4 times duct diameter squared. So the velocity in the duct can be expressed as 4 times airflow divided by pi times diameter squared. This means that the airflow velocity in the duct can be adjusted by changing the diameter of the connecting ductwork. And this is exactly what ventilation engineers do. They use the largest duct diameter that provides the minimum transport velocity. Higher velocities simply require more power and ultimately cost more money to operate. Air cleaners serve, obviously, to clean the air. How well they clean the air depends on the purpose. If the air is being exhausted outside, then they need to be designed to meet air pollution regulations. Alternatively, they need to be effective enough to protect workers if the air is recirculated back into the facility. Air cleaners also serve to protect the fan, as some gases are highly corrosive and some particles can erode the fan blades. There are many different types of air cleaners depending on the contaminant being cleaned. Spray towers are used to absorb gases. Granular beds can be used to adsorb gases. Cyclones and bag filters are common air cleaners for particles. I will spend some more time on hoods, as they are the point of entry into local exhaust ventilation system. There's a wide variety of hoods available, with a selection depending strongly on the operation being ventilated. We will review hoods in the following 3 categories. Enclosing hoods completely or partially enclose the source of the contaminant. Capturing hoods use the airflow of the exhaust system to reach out and capture the contaminant. Receiving hoods are aligned with the energy of the source that helps them receive the contaminant. We need a few terms introduced before starting. We've already introduced duct velocity, which when multiplied by duct area gives us airflow. As shown at left, the source is fully or partially enclosed in an enclosing hood. Typically, the face velocity is specified for these hoods to ensure the contaminants from the source do not enter the workplace. As shown at right, the source is located outside of a capturing hood. In this case, the velocity of the air at the source, referred to as the capture velocity, must be sufficiently high to pull the contaminant into the hood. Oftentimes, capturing hoods use slots to ensure adequate capture velocity across a wide area. If so, the velocity of air entering the slot velocity, and velocity downstream of the slot, the plenum velocity, are usually specified.